Good morning, everybody. Today we're going to talk a little bit more about these classes we saw last time, Merlin Arthur classes, Merlin Arthur MA and Arthur-Merlin AM. And we'll see a few things that I alluded to last time. So one thing we'll talk about today is constant round interactive proofs. So these are sort of like baby versions of interactive proofs where, you know, there's maybe only a couple of messages between this prover Merlin and this verifier Arthur. You can imagine, you know, longer conversations, and we'll see that constant round public coin interactive proofs actually all can be compressed down into just the class AM, where Arthur sends one message and Merlin sends one message. In next class, we'll actually see that this public coins thing, this is the situation where Merlin can actually see the coin flips that Arthur uses. It's not important in the sense that it'll be equivalent if Arthur has private coins. So Arthur can like hide the coin flips that he uses from Merlin. Okay, and so we're going to talk about that, and it'll take a while. And there's going to be a lot of the letters and the backwards R's, and you might be like, wow, we're really getting into outer space here. Like, what does this have to do with my life? But we'll end the lecture with a couple of kind of quick but nice applications that teach us things about like more basic complexity classes. So, you know, when we initially studied the polynomial time hierarchy, we motivated it by, you know, asking you just like, okay, suppose, you know, you should always think about this possibility. Suppose NP can be solved efficiently, then what other problems can we solve efficiently? Okay, and we saw that if NP is in P, then actually all the languages in the polynomial time hierarchy are also solvable in P. But we should sort of ask the same question if our, you know, notion of efficient computation is randomized computation, BPP. And another thing we'll address at the end of the class is you know, a simple question that we can kind of get a good answer to through studying these Arthur-Merlin classes. And that's the question of whether this graph isomorphism problem could be NP complete or not. Okay, so we'll come to that at the end, but let me return back to where we were last time. So last time we had introduced these two classes, MA and AM. And we also had this like somewhat crazy notation to describe them. So MA, we had this notation for. I'll remind you what that means. So, okay, first of all, this quantifier means for most. You can think of it as meaning for most, for at least 2/3 of the strings. Again, Merlin Arthur MA was the class where, you know, you're in the language. If there's something Merlin can send you that you can, like a kind of certificate he can send you that you can confirm in probabilistic polynomial time. And if the string is not in the language, then no matter what Merlin sends you, you can like disconfirm it in probabilistic polynomial time. Okay, so that can be expressed with these quantifiers. So what that really meant, the longhand version of this shorthand, is that a language L is in the class MA if, and I'll expand this out, when X is in the language, there exists some string Y, you can think of it that Merlin sends, such that for most random strings Z that Arthur uses, Arthur's verification accepts. Okay, so where V is a deterministic algorithm, or you can think of it as a random algorithm that takes X and Y as inputs, and Z is the random coin flips. And conversely, if X is not an L, then no matter what Merlin sends for all Y, for most random strings that Arthur uses, he'll catch Merlin in a lie and reject. Okay, so this exists for most is here. This for most is down here. And we always have deterministic polynomial time algorithm equaling 1 and equaling 0. Okay, and there's still a shorthand because really this means there's like some polynomial length bound for Y and Z as a function of the length of X. And it's also implicit that V is a polynomial time algorithm, but I didn't write everything, all of that everywhere. Okay. And similarly, the class AM was sort of the reverse of this. So it was for most exists, and for most for all. Okay, so this is kind of the class where Arthur goes first, and he kind of chooses you can think of it as Arthur chooses like a random challenge for Merlin related to the input X, and then Merlin can send back a string, and Arthur can see if that convinces him that the X is in the language. Okay, so we proved two theorems about these classes last time, we proved that MA is a subset of AM. Okay, so you can decide more languages with this kind of protocol than with this kind of protocol. And the other theorem we proved was actually just about, well, we proved actually a couple of things. We proved that these classes are equivalent to their versions where there's one-sided error. And the route we took to do that was involved actually looking at BPP. Okay, so BPP is just sort of the class where Arthur's all by himself. There is no Merlin. And so you can write in our funny notation like this: for most. So when X is in the language, for most random strings, the verification accepts. And when it's not, for most random strings, the verification rejects. And right, so the theorem that we proved out BPP is actually, it was equivalent to a different version, or it's contained in a stronger version if you want. This for all, for most for all, and for all for most. And I'll remind you of that just now. OK, so this is one class. And then also, BPP is closed on their complements. So we can interchange these. That's how you take the complement of this class, interchange these two pieces, and get another fact. Okay, so I'll label this fact A and this fact B. Okay, so we proved these two things last time. And actually, let me just go ahead and tell you now how that went, or remind you how that went. OK, so the idea is when we want to prove this kind of decisive characterization of BPP, first we did error amplification for BPP. So we just assumed that the error probability, instead of it being 1/3, was like 2 to the minus n or something. We can always do that. OK, so then we got into a situation for a particular language L in BPP where if X is in the language, for an overwhelming fraction of the random strings R, well, I wrote it here not as a verifier accepting, but as R being in this set capital S. Okay, so I'm imagining if we have this language L, there's a fixed deterministic verifier V, which takes the real input X in a random string R. And I'll let S be all the random strings where it accepts. Technically, it depends on X, but let me not show that notation. OK, so the property that this verifier has is that when X is in the language, S is huge. Almost all strings are in S. I guess this is the S is huge picture. And when X is not in the language, S is tiny. So almost no strings are in S. OK? And then we saw when we were in this situation, we decided to consider a set U, which looked like a bunch of shifts of S unioned together. OK, so we imagined shifting the set S by XORing it with some string W that sort of just translates it around, and unioning that with S shifted again. OK, and unioning that with, actually it was convenient to take exactly P shifts of S, where P is the number of bits in the random strings R. And what we observed is that if you do this, you know, a couple of different things happen depending on whether S is huge or small. So if S is huge, we observe that for almost all shift sequences, the set U is everything. It covered up everything. OK, so what we could say there is that for all Z, Z is in U. And on the other hand, if F is tiny, then even if you take a bunch of shifts of tiny set and union together, you still have a tiny set. So that meant actually for all shifts, most strings were not in U. So for most Z, Z is not in U. OK, so you see this pattern of quantifiers that's over there for most for all, and for all for most. OK, and finally, kind of writing right to left today. Finally, this condition Z in U, what does it mean? Well, if you think about it, it means that W1 XOR Z is in S, or W2 XOR Z is in S, or dot dot dot, or WP XOR Z is in S. Okay, the crucial point is that this is checkable in polynomial time. Deterministic polynomial time. Okay, so in other words, if we sort of change the verifier from V to a deterministic verifier that checks this Z and U, then we get an equivalent characterization for BPP, which has this for most for all for most thing. Okay. And if we change the verifier to check that Z is not in U, the opposite, that's how we would get this, right? Let's say like when X is in the language, for all shifts, for most Z, it's not the case that they're, wait a minute, does that make sense? Somehow we're just formally reversing these two segments. So why do I bring this up? I want to remind you of how we use this to get one-sided error for MA and AM. Actually, let me just skip. We saw MA, why you get one-sided error for it last time. And I kind of, at the very end, blurted out how you get it for AM. But I want to review that a little bit here. So here's how you think you might get it. So this is our characterization of AM. And it kind of looks like, in fact, it is sort of like NP, but with like a kind of a for most quantifier stuck at the front. So you might kind of think to yourself, oh, you know, here we kind of saw that you can change this quantifier in this way. So let's kind of imagine we can do that and see if that makes sense. So what happens if we just sort of try to replace this for most here with this characterization? We actually have two choices. We could do this one or this one. So it would seem then that AM, perhaps by virtue of A, I'll put a question mark here, is a subset of, let's see, for most for all exists, for all for most for all. And I put a question mark because we kind of have to think a little bit about whether this is true. What I've done here is just kind of tried to replace this for most with this characterization here. In a second, I'll ask if that really makes sense. But supposing it does make sense, it turns out it will, then we would get this characterization. This characterization turns out to be true, but it's not really that useful. So I'll mark it with a sad face. But we can also use the code version of it, the opposite version. And again, if we believe we can kind of just do this substitution, we would get that AM, again, if we replace the for mosts here by this characterization, we would get for most, for all, for most, and for most. Yeah, there should be a sort that exists somewhere. Thank you. This is very hard.
For all RE.
Thank you. For all. For most. Good. Now I put the exists. I ran into the exact same trouble last time. I should just practice this like over and over. For most, for all, for all. Phew. OK. Does that look good? All right. And now the point is that, yeah. That's right. So this we can weaken, you know, for all something. Let's say for most Z, there exists a W. We can weaken this to there exists. And we can combine these. Okay? And so therefore, this is a subset of for all exists slash for most for all. Okay? If you think about it, this is like AM with one-sided error. Okay, so here the situation is like for all random strings that Arthur chooses, there exists something Merlin can say that will convince him. And here, when it's not in the language, it's like for most random strings that Arthur chooses, there's nothing Merlin can say that will convince him. Okay, so we have like error on this side and like no error on this side. Okay, that's a lot of work, but somehow it seems good. Good to know. But actually, we still actually have this issue, which is that, you know, I kind of did this replacement syntactically without thinking exactly if it makes sense. So we have to think about like whether we can do this. Like in some sense, we replaced this. The only thing that was left here was like polynomial time computation. But in AM, what was sort of left here was like an NP kind of computation. So what are the ingredients that we used here in order to like make this switch with the translates and the union and everything? So let me ask. This one we like, so I'll put a happy face. So what I want to do is ask myself whether this is actually legal. So let's look at these two guys. Actually, let's justify sad face. Not because we need it, but somehow I think it's like a little psychologically easier, as you'll see in a second. The proof will be the same. So I'll justify sad face, even though it's not such a great result, but you'll see that the proof will be the same. So let's look at what we tried to do up here. We had like this was AM, and we tried to replace this for most with this thing. So as I was saying, it's really like BPP, except now we have like an NP computation on the inside here. So this kind of V is like an NP computation rather than a P computation. So there's two ingredients that we used in the proof. So first of all, in this AM definition that we start with, can we do the error amplification? Okay, to get exponentially small error, like we did when it was BPP. And let me just say the answer to that is yes, and I'll explain it later. Okay, so there's a couple of things to explain here, but let's say yes. So we'll see it. So you'll get into the situation where in AM, if you have a language in L in AM, it has a characterization where for like an overwhelming number of strings that Arthur sends, when the X is in the language, there's something Merlin can say that will convince him. And when X is not in the language, for an overwhelming set of strings he sends, nothing Merlin will say will convince him. OK, so that's good. OK, now the issue is like now, this set S that we talked about over there, instead of being like the set of R's such that some deterministic verifier accepts, it's kind of like it's kind of like the set of R's such that a non-deterministic verifier would accept. Okay, or we might say it's like the set of R's such that X comma R is in set. And now we have to observe. We can try to do the same trick. We have to look at this thing, which I mark as dagger. If we make a bunch of shifts of this kind of S and define U in that way, is this U checkable in non-deterministic polynomial time? That's what we have to kind of check. So is it? It's going to be, yeah, or else I wouldn't have asked. Yeah, it is, because, but it used the fact that perhaps you're familiar with now, that sort of NP is closed under kind of union, and not just union, but union of polynomially many things. So if you have some statement like, I don't know, a certain string is in a set S, that's like an NP statement, then like unions of statements like that are also an NP. Okay, because like to be convinced of a statement like this, you just need to get a certificate for at least one of these things, these substatements, because it's an OR, and there's polynomially many of them. And it's also true that it would be the same situation if these were ANDs. You can become convinced of an AND of a bunch of NP statements just by having the verifier sending you witnesses for all of them. Okay, so NP is kind of closed under polynomial ORs and ANDs, or unions and intersections. And we kind of need that fact to carry out this kind of shift-based amplification. Okay, so it is deciding C and U in NP. Well, as I described, the answer is yes. Okay, so I want to be a little bit careful here to explain why you can do these. It's tempting to do these like syntactic translations, but it actually takes a little bit of justification to see why they work. Okay, so that sort of completes the proof. Well, modulo this, which I didn't tell you yet, but it completes the proof that AM is equivalent to AM with one-sided error. Yep.
Is there any like general theorem that you can do whatever you want syntactically?
Yes, basically there are general theorems that say like you can do whatever you want syntactically. Like the ways that you hope you could manipulate these statements are justified. It still takes even more justification. This justification is like often skipped if you like look at like lectures about these topics. So I'm going to actually tell you a little more of the justification later because it breaks my heart to like lie to you all. But it's ultimately pretty boring, so I'll mostly sketch it. Okay. Any more questions? I mean, the takeaway after all this, what you should remember in 10 years is just that, if you have a 2-round interactive protocol where like Arthur says something and Merlin says something, then you can actually upgrade it to get one-sided error. That's nice. Okay, so as promised, I'm now going to talk about constant round interactive proofs. So, you can think of MA and AM not really in terms of interactive proofs. Like we initially defined MA as like, well, it's just like NP, the verifier gives you a proof, and we just let the checker be randomized rather than deterministic. And AM we kind of actually initially defined as like, oh, it's the things that are randomly reducible to set. But it'll be good now to like think of these Arthur-Merlin things in terms of actual, interactive proof systems between two parties. Okay, so if you've seen interactive proofs before, this will be a subset of them. So we're going to be talking about constant round and public coin interactive proofs, or Merlin Arthur proofs. Okay, this is a very interesting topic in complexity. I mean, it's quite interesting, as it turns out, to like model what kinds of statements you can prove, not just in like the classic NP way, where like you get a witness and you check it, but with kind of interaction or some kind of teaching. So the setup here is that you have a language L and a string X, and you're always curious about whether the string X is in the language L. And there's two characters in the story named by Babai. There's Merlin and Arthur. And the kind of point of view you should have in mind is that Arthur's curious to know whether X is in L or not, but like he has no like, preference or anything. He's kind of indifferent. He's just like, I want to find out what the deal is. Whereas you should imagine like Merlin's motivation is always to like convince Arthur that X is in the language. Even if it's not in the language, like Merlin really wants to do his devious best to convince Arthur that the string is in the language. Okay, so their characteristics are as follows. So Merlin is, you can imagine, all-powerful. I mean, we don't count his computation time or anything against him. He can do as much computation as he wants. He can see Arthur's coins. So this is, I should mention Arthur is randomized polynomial-time. Okay, so he's an efficient algorithm. Albeit he's allowed to use randomness. Merlin can see Arthur's coin, so that's why it's called public coin. And, next class we'll see that actually this doesn't make a difference. And as I mentioned, Merlin's always trying to convince Arthur that X is in the language. Okay, so what we imagine they can do is, like, they're both sitting there, like X comes out, and then they can talk to each other. They can send messages. So like Merlin sends some message, just kind of like a Y, to Arthur. Then Arthur sends some message, probably a randomly chosen one. Because if Arthur behaved deterministically, then Merlin would just know what Arthur is going to send. So he can say, let's eliminate this message. And then Merlin might send something back, and Arthur might send something back. Maybe Merlin might send something back. And then maybe at this point, like Arthur says accept or reject. Vis-a-vis whether Arthur is convinced or not that X is in the language. Okay? And we say that I want to say, this kind of protocol is called, temporarily, we'll call this an MAMAM protocol. Okay, MAM because it has 5 rounds, and Merlin speaks Arthur-Merlin, Arthur-Merlin. Okay, and we're only going to be talking about constantly many rounds here, like 5, 6, 3, whatever. You can change who speaks first, and well, who speaks last is determined by the parity of the number of rounds. Okay, and so for example, we'll say that a language L is in this class MAM if there exists a protocol like this, i.e., there exists, a randomized Turing machine A here, and like some answering person, Merlin here, such that when X is in the language, it should be the case that there exists like some Merlin that will convince Arthur, so that such that the probability that Arthur eventually accepts is at least, let's say, 2/3. And if X is not in the language, then like for all Merlins, the probability that Arthur accepts is at most 1/3. Okay. And later we'll see again that like the language, the definition of the class doesn't change if you change these 2/3 to anything like in BPP, polynomially bigger than a half or exponentially close to 1. Okay, let's think about this for, yeah.
Do all messages need to be polysize?
Yeah, so really, all messages have to be polynomial size. So really, like the protocol is actually specified by like a polynomial length bound for each of these 5 messages. Yeah, and Arthur's behavior. Yeah, so again, just to give you an example, I mean, we'll see more examples actually next lecture, but if we just change this to private coins, then there's like this well-known AM, just 2 round style protocol for graph non-isomorphism. Remember, we have 2 graphs, and Merlin's trying to claim, or always trying to convince Arthur that they're not isomorphic. And Arthur challenges Merlin by picking one of them at random, randomly permuting the vertices, sending that message to Merlin saying, okay, which one did I pick? And Merlin has to guess which one he picked. Okay? So you can kind of tell that it has these 2 properties, except that it relies on the fact that Merlin doesn't get to see Arthur's random coins. But it's kind of amazing, actually, that you can get the same kind of thing in a public coin way. Okay, so I want to make some remarks about these kinds of protocols. So the first claim that I want to make, and this will be an example of something I'll kind of claim without really getting into the details. In some sense, they're easy. This complexity class, or any similar one, with any fixed number of messages, has efficient error reduction, just like BPP. Okay, so as I said, these constants are not important. You can boost them exponentially close to 1. And why is this true? One thing you have to be a little careful about at first is, like, you might say, oh, okay, if I have this 5-round protocol that achieves error 2/3, maybe I'll just repeat it 10 times and drive the error up, down. And then it becomes like a 50-round protocol, which is maybe not desirable. But you can actually stay within 5 rounds. Anybody have a suggestion on how to do it? Yes?
You do like alt and then parallel.
That's right. You do it by parallel repetition. Now, as we'll eventually, or perhaps later, see in complexity theory, if somebody claims to you that you can decrease error in like a protocol by doing parallel repetition, you should be very skeptical, because there's a famous case in the history of complexity theorem where that was like claimed, and like the claim went unchecked for a year, and then it turned out to be like grossly wrong. Well, actually, it was true, but the proof was extremely insufficient. But it turns out that like this one is fine. So basically, you just imagine like, I don't know, let's imagine like a 3-round protocol like AMA. Arthur talks and Merlin talks and Arthur talks. We really are just going to have Arthur say like, let's repeat this protocol 100 times in parallel. So instead of me sending you 1 random message, I'll send you like 100 random messages, independently drawn. And then you, Merlin, respond with your 100 responses, and then I'll, do my 100 random checks. And you might think that like maybe Merlin could do something better than the naive thing here, because Merlin can kind of see the 100 different questions he's asked in the first round, and maybe he could coordinate his answers or something. But basically, no. Like, you know, Arthur's always playing independently between these like 100 copies of the game. And so like Merlin should just always sort of do the best thing he can on each copy of the game. And so just act in the way he would act if it was like a non-repeated version of this game. Okay, so I'm not going to like write any words or anything, but it turns out that like you just do the same thing you do for BPP. You play the game like maybe 100 times in parallel. You know, all the message lengths go up by a factor of 100. And at the very end, Arthur like takes the majority of the accept-reject decisions he would have made. And it gets amplified just like in BPP. Yep.
So is the efficient error reduction not as strong as BPP? Like you can only get it down to a constant because you can't repeat polynomially many times.
No, you could still get it down to exponential because you can repeat. You can still repeat polynomially many times. So like, you know, like if before like the situation where like Merlin sent one message here and then Arthur sent a message and then like Merlin sent a message, we'll repeat it. You know, you can have like Merlin send like, you know, n squared messages, and Arthur will send back, you know, I picked n squared as sort of like a random polynomial, n squared messages, and so forth. So all the message lengths blow up by a polynomial amount. You still have the same number of rounds. And then kind of at the end, like Arthur thinks to himself, OK, like would I have accepted or rejected here? Would I have accepted or rejected in this version of the game? And he takes like the majority of all these answers. Somehow you look on.
I guess my follow-up question is, what exactly is the constraint on the size of messages that can be sent back and forth?
They should be polynomially bounded in x, length of x.
Okay. But we're not dealing with a fixed polynomial or like.
I mean, you have to change the nature of the interactive protocol, but like so L is in MAM if there exist 5 polynomials P1, P2, P3, P4, P5 which bound these lengths, and a polynomial-time Arthur algorithm such that this stuff happens. So like when you do the parallel repetition, like those polynomials become larger polynomials, but they still exist. Yeah. Yep.
So Merlin can simulate Arthur, right? Like because Merlin has unbounded power, and Merlin can see Arthur like coins.
Yeah. Well,
Merlin can see
Arthur's coins. Yep.
Okay. So like I'm thinking like in the last step of the step, like say if you're doing this parallel repetition, then Arthur asks like 100 questions and Merlin sends 100 responses.
Yeah.
Merlin knows that Arthur is gonna somehow take the majority of them.
Yeah.
Then couldn't Merlin like cheat and kind of like say structure responses so that all of them are make it like, Arthur accept, or is that not possible? Am I?
Yeah, I mean you're right to be skeptical and like. But basically, like, we'll see actually in maybe a little bit more detail in a second. But like, basically, it's always within like in Merlin's best interest to like say the best thing he can, like vis-a-vis making Arthur accept. Like, I don't quite know how to put it besides that. Yeah.
I think this is similar. So when we say Merlin's all-powerful, he can't solve halts though, right? Or can he?
I guess he can. Like really, Merlin is on one hand, so really Merlin is modeled by a function.
Oh.
Just so he's like modeled by like a function. Merlin is some function. Let's have Arthur speak first. So like Merlin is just some function of x in the first message of Arthur, and we're asking about the existence of such a function. As it turns out, we'll see maybe later that it's equivalent if we merely give Merlin, let's say, the power of p-space. But in principle, like it could be any function. Yeah?
One question.
Yeah.
Does it make sense for Arthur to like send a message last?
It doesn't make sense for Arthur to send a message last. I'll get to exactly that now. It does make sense to allow Arthur some randomness at the end. So in some sense, it doesn't make so much sense for Arthur to send a message last. But it's kind of like in like MA, right? Like Merlin sends a message, like his witness, and then you allow Arthur randomness. Let me clarify one thing now, and maybe that'll help. So in some sense, it doesn't. The way I've described it right now, it doesn't exactly make sense to have like Arthur send a message per se. But let me say, like without loss of generality, all of Arthur's kind of, I'm being a little bit casual here, but like all of Arthur's deterministic computation can be moved to the end. Like you kind of think of like Arthur, maybe he flips some random coins, does some computation, flips some random coins, does a little computation, and finally sends a message. Wow, OK. But what you can imagine, I'm saying without loss of generality, that Arthur literally just flips coins and tells those coins to Merlin, and then says, like, Merlin, you figure out what I would have done, right? So what we're trying to say is, without loss of generality, Arthur, let me say 2 more points, and then I'll take the questions. Arthur just flips coins and sends them to Merlin. And I want like that to be like everything that Arthur does. So like another thing you can kind of set it up, make without loss of generality is that like after all the messages, a deterministic referee, polynomial time, V, takes the transcript and outputs accept reject. This should be polynomial time. OK, so we really, in this version of it, like reduce Arthur to just a person that flips coins and tells them to Merlin. And even at the very end, like instead of imagining like Arthur being the person that like looks back at everything that's happened and decides to accept or reject, we just have like this other fixed third party V, like look at the whole transcript and decide whether to accept or reject. And in this context, it makes sense to like have Arthur send a final message. Like Arthur generates like one more set of random bits to kind of help the verifier make a random decision. To use a random algorithm to make its decision. OK. Questions?
I was going to try to answer that question because like Merlin cannot simulate everything because Arthur made flip random coins after Merlin has sent his last message, right?
Yes.
So that's Merlin's time.
Right. Yeah, maybe I should have. It's hard because it's not so easy to give like a nice example of this, except for graph non-isomorphism, but that has a property that like you need private coins. So like one thing that we'll see next time, like maybe a good thing to have in mind is like maybe we'll see this next time. Imagine that Arthur and Merlin are both looking at a circuit, and Merlin is trying to claim that this circuit has many, many satisfying assignments. And let's say like we're in a weak situation where like either everybody knows the circuit either has many satisfying assignments or very few. Okay? And Arthur is just trying to figure out, does it have tons of satisfying assignments or few? We'll see next time like Merlin can like send Arthur like a satisfying assignment, which Arthur can check, but Arthur's like, well, that's just one satisfying assignment. It doesn't prove very much. We'll see like this kind of protocol. Like Arthur will like choose like a random hash function that hashes n bits down to like some medium number of bits, and kind of ask Merlin, tell me a satisfying assignment for the circuit that hashes to the all zero string. Okay? So if there's like tons of satisfying assignments, then Merlin will be like, no problem, I can do that. Whereas if there's few satisfying assignments, Merlin will have a very hard time doing that. Okay, so this is a way like Arthur can like try to decide, does this circuit have lots of satisfying assignments or few? And this is like a case where like it's public coins. That's critical. Like Arthur doesn't care if like Merlin sees his coins. In fact, he's just going to kind of pick the random hash function and tell it to Merlin. So that's a scenario you can kind of have in your head where like it kind of makes sense that like Merlin just kind of indifferently like flips some coins, tells them to Merlin, but then Arthur kind of checks Merlin's ability to respond to this random question. So we'll see that in more detail next time. Yeah.
So if Arthur is just flipping coins,
yeah.
Why can't Merlin just ignore why can't he just do all of his computation at once?
Merlin can't do all of whose computation? Sorry, can you just repeat the question?
Yeah, what I mean is, like Arthur flips a coin,
yeah.
Merlin sends a message back to Arthur.
Yeah.
But why can't Merlin just wait until he sees all the coins and then sort of send his messages back all at once, and then you only have 2 rounds instead of...
Well, eventually we'll see that actually it can be that way, but it's not obvious. I mean, the point is that like, I don't know, like the interaction could potentially help Arthur, like, you know, it's kind of like it's like a back and forth. I challenge you to like, you know, tell me a string that satisfies this, you know, circuit and hashes to this value, and you manage to do that, and then, you know, I might want to keep further questioning you. Like maybe I'm not satisfied. Like maybe I want to like, I don't know, like engage in a binary search with you to kind of maybe pin down roughly how many strings satisfy this circuit. So we might need like sort of multiple interactions.
Can we still think that way if he's just flipping coins and sending them?
You really, I mean, it's seemingly you really do have to like, seemingly you can do more with this interaction where like Arthur like chooses some challenge, Merlin responds, Arthur chooses another random challenge, Merlin responds.
I think the reason why this isn't obvious is that the first message can only depend on the first coin flips, and the second on the two first coin flips, and this wouldn't be equivalent if we would just send one message in the end.
Yeah, maybe I didn't make that more clear. That's a very good point. So like really Merlin's modeled by like a function, and like Merlin's message, forget all this stuff, like Merlin's first message, let's say this is like A0. Merlin's first message, M1, is any fixed in advance function of A0 and X. And then like Merlin's next message, M3, is like some fixed in advance function of A0, M1, A2, and X. Okay, so like the key thing is, Merlin, when he's sending a message, he cannot, one thing he doesn't have the power to do is like predict what coins Arthur will flip in the future. He can see the coins that Arthur's flipped in the past, but he can't predict what coins Arthur's going to flip in the future. That's one kind of limitation that he has. Yeah.
Last time we said that we get round compression for AM, right?
We're going to talk about now why this turns out, by like an interesting fact, to be the same as AM.
Okay.
But it's not obvious.
So we get round compression no matter whether A starts or M starts?
Yeah. Okay, so let me get into that. Actually, one more thing that you should kind of try to check is that like MA and AM as defined this way are in fact the same as like MA and AM defined this way. What? They are. I mean, but it's not like 1,000% obvious, but it's true. Okay, so indeed, when in the paper where Babai introduced these classes, he also showed that in fact, you know, MA, it doesn't matter. Any fixed number is actually equal to AM. Except, okay, yeah, greater than or equal to 3. Okay, so AM and MA we don't know are the same. And like if you have like just A, that's BPP, and we don't know that's the same. And if you just have M, that's NP. But as soon as you have like anything more than MAM or anything more than AM, it collapses down to AM. And I should mention, like, you know, I mean, if a language is in AM, then it's also in the same class when you add more letters. So like it's also in this because, you know, the protocol can just ignore the first message that Merlin says. Okay, so this is actually an interesting case where you could like imagine defining a hierarchy, but it actually all collapses. It's very important also that this is only a fixed number of rounds. It turns out you can imagine that like, you know, the same scenario, except they're allowed to talk for a polynomial amount of time with polynomially many messages back and forth. That's presumably a different class. That turns out to equal p-space, as we'll eventually see, which is much bigger, presumably, than AM. So here's an idea with a question mark for the proof. Okay, so like, you know, yesterday or last time we proved that MA is a subset of AM. So you could just be like, well, let's look at, I don't know, AMA. Hey, like here's the AM part. Or sorry, let's do it this way. Here's the MA part. And we know that like MA is a subset of AM. I'll put a question mark here. So we could just replace this part with like the AM version and get this. And then you can always collapse A's and M's, right? Because it's like Arthur flipped some coins and then Arthur flipped some more coins. So this is AM. And you might say, oh, okay, what about MAM? Well, again, like, oh, here's like a little MA piece. I'll just switch it to AM. And I have like AM, M. And that's just AM. Because again, Merlin sends something, and then Merlin sends some more things. You could just collapse that to Merlin sends some stuff. OK, or like if you have AM, AM, you might say, oh, I'll switch this to like AM. OK, and like everything just collapses down to AM. On one hand, this is sort of the idea. On the other hand, like at this level, it's not correct. But you'll find like multiple places where like this is just written, and there'll be like end of proof. But it's wrong. To justify it's like a little bit complicated, so I'm not going to go into like literally 100% of the details, but I'll do some of the details, and then we'll just decide that it's true. So let me sketch the correct proof. And actually, this will help a little bit maybe to understand these classes. Let's say, I don't know, let's take AMA. Okay, so let's say L is a language in AMA. It has this AMA style protocol. Okay, and let's say you're given some X. What I want to actually reason about is like, in some sense, this fixes V. This referee down here. I want to reason about like, for a given X, what is the probability at the end that X is accepted? And in AMA, you should kind of draw this picture. Like, we have Arthur, and in the first round, there's like many messages that he might send. We'll call these Ys, and he chooses one of these messages randomly. Okay, and then sort of in the second round, you have Merlin, and there's like many choices for what Merlin could send. Okay, and he chooses one of these kind of optimally from his point of view to make the acceptance happen. Let's call that second message Z. It's AMA, so there's only one more round. So finally, like Arthur, maybe it's a bit funny to call it a message, but like he sends some random string, which we'll call W. And again, he's like an indifferent player, so he just chooses a random string. Okay, and finally, after all these three messages have been sent, you look at what V does, this referee on Y, Z, W. This is the transcript, Y, Z, and W on input X. It either accepts or rejects, which I'll mark with like zeros and ones. Okay, so like for all these leaves here, you can just write down whether the verifier or referee would accept or reject. Now, how do you compute the overall probability, or rather like the highest probability with which X is accepted? I'm not saying this perfectly, but what you should do is, whenever you have like a node like this, an Arthur node, you should kind of like average, we'll put a capital letter, average over the children. In the sense that like, OK, if the protocol has got to this point, you're asking yourself, OK, what's eventually going to be the final probability of accepting? Condition on kind of getting to this point, like seeing Y and Z in the transcript. Well, it's just the average of these zeros and ones, right? Because the last thing Arthur does is flips a coin, and then the verifier says 0 or 1 based on that. On the other hand, when you have like an M node, when Merlin's talking, you should take the max of the children. Okay, and that's because like Merlin is always trying to like get the highest probability of the thing being accepted. All right, so like when it gets to here, like Arthur sends Y at the beginning, Merlin's like, huh. OK, if I send this string, then the probability Arthur or the verifier will eventually accept is like whatever the average of this child is. If I send this string, it's whatever the average here is. So he kind of looks at all these strings and picks the one with the highest average. And that's what he outputs. So it's kind of like you take this tree and like you average here and you max here. So maybe Bilbao had that in mind when he chose Arthur and Merlin as the names. You average here. And then finally, like the number coming out here is like the overall probability that the protocol accepts X. Now, as I told you before, if you think about it for like 1 minute, you can do a Fishin error reduction. Okay, so in an effort to try to prove like this, the first thing I'll say is like take a protocol that shows a language is in this class and do like a Fishin error reduction on it. It's parallel repetition. So I'm just like sketching a proof here. So like you can assume that on top you have something like, Arthur is spitting out a number which is either super close to 1 or super close to 0. Okay, like theoretically, according to the definition, it just has to be bigger than 2/3 when x is in the language and less than 2/3 when it's not in the language. But after error amplification or reduction, you can get really close to 1. So let me just imagine one case. Say that actually x is not in the language. So what I'm saying is you can assume that on the top, after error reduction, that you have that this number is like less than, let me say, 16 to the minus n, where n is the length of x. Okay, so like the first thing we do is like amplify the success probability like crazy, so that when like x is not in the language, Arthur actually accepts with probability less than 16 to the minus n. So why do I do that? The point is now, what we're saying is in this circumstance, we have the average of a bunch of numbers, and the average is super tiny. What that means is almost all the numbers down here are super tiny. Okay? So it's not just that the average is small. There's kind of a stronger property qualitatively. Almost all the numbers are small. In particular, you can see like at most a 4 to the minus n fraction of like these incoming probabilities are bigger than 4 to the minus n. Okay, because if more than 4 to the minus fraction of them were more than 4 to the minus n, like their average would already be more than 16 to the minus n, even if they were just barely 4 to the minus n and all the other numbers were 0. Okay, so after error reduction, you can kind of show that like not only does Arthur have like a high probability of winning, it's kind of like qualitatively better. For almost all strings that he might send, he still gets into a situation where he has a very high probability of winning. Okay, it's not just like, oh, like, I don't know, 50% of the time he has a 99% chance of winning, and 50% of the time he has a 40% chance of winning. That would overall be 70%, which is bigger than 2/3. But like, it kind of sucks because like half the time he actually gets into a losing situation. But if you really amplify the error, you can get into the situation where like sort of at every node, like almost all the children are like super close to having the right, the target probability like close to 1 or close to 0. Okay, so again, I'm being a bit sketchy here because I don't want to write like everything. But you can do this kind of amplification argument at like all nodes in the picture, so like even these ones down here. So let me just get to the punchline I want to get to, which is that you can sort of repeat this argument everywhere. And what I want to get to is this, that like AMA is exactly this class. For most exists for most slash for most for all for most. Okay, that's not obvious, but like this is somehow like a stronger statement than this one. This just sort of says like overall in the protocol, like Arthur has like a 2/3 chance of getting the right answer. Or the verifier has a 2/3 chance of getting the right answer. But it could be that like, oh, he gets some advantage here, which is compensated for some other advantages or disadvantages here. But this version really says that like for almost every first message, there's something Merlin could say that so for the almost every third message he accepts. Does that kind of make some sense? Kind of don't want to belabor the point too much because it's a little bit boring. But so similarly, this class is, for most or exists for most or exists for most slash for most for all for most for all for most. Okay. So that's good because when we proved, last time when we proved MA is a subset of AM, it wasn't. These were like kind of code names really for exists for most, for all for most. And this was code name for like for most exists, for most, for all. Okay, so we didn't really show that like in the middle of some 2-round protocol you could do this switch. We just showed that like this complexity class is a subset of this complexity class. But that's the kind of thing we need to like switch things on the inside here. Now, as we saw earlier when I talked about getting one-sided error for AM, it's still not immediate that like if you have this, you can just like switch two of them. That's the thing you want to do, right? Like you want to say, oh, in AMA, I want to say that whenever I have exists for most, for all for most, which is here, I can switch it to, you know, RE, RA. You know, that'll give me like R, RE, R, R, A, and these compress, and we get like this is for most exists, for most for all, and this is AM. Okay. Even, you know, as I said before, it's like not so immediate that like you can take this fact and switch it with like it's in the middle of quantifiers like this. But you can do it. You have to check that like, you know, it relies on the fact that you have like this error amplification, so you can make the errors really small. You have to kind of look back at the proof of why MA is a subset of AM, which if you recall, like first you amplify the error a lot, and then you just say, hey, let's let them switch messages. And like now when Arthur sends his message before Merlin, you know, if Arthur's probability of like winning was so high before here, yeah, then you have to look back at the proof. Then like, you know, there's nothing Merlin can do even if he can see Arthur's message first. Okay. Yeah, I don't really want to get back into it, but like if you go look back into the proof and use the fact that like even in like these classes you have like efficient error amplification, you can like repeatedly do it everywhere by parallel repetition, you can show that it is okay to like switch these this for this in the middle of a string of quantifiers. Okay. Kind of sounds like if I say like any questions now, I'm like secretly don't want you to ask questions because I want to get through with it, right? But I'll take them. Any questions? Let's do it.
There is an exist sign in there. So if you end with Merlin.
Pardon me?
So if you end with Merlin, let's say AM, AM.
Mm-hmm.
So you have exist in there.
Yeah.
Is that obvious that you can throw it away or not?
Okay, the idea is, right, is that if you have like AM, AM, that's really like, I mean, if you want to translate it into this, it's like, you don't actually throw it away in the end. So the way like you get this down is you first replace this with AM. Because MA is kind of because MA is a subset of AM, and so you've shown that this is a subset of AAMM. And then it is okay to just sort of say, well, this is just AM, like Arthur and then Merlin. You can look at it this way, right? Like, I mean, if Arthur chooses some random coins and then you average again, it's really just like averaging over more random coins. And similarly, if like Merlin maximizes over one message, and then he gets to send another message, which you can also maximize over, you can just compress that into like one longer message that Merlin maximizes over. Yeah, so you can never get it down to like MA, but for any string of like A's and M's, you can get it down to AM. Somehow, yeah, like this is the trickiest case. You know, you switch this and you get AMM, which is AM. Okay. Any more questions? Okay, so you can again, like in the rest of your life, forget that nightmare, and just remember the fact that constant round interactive proof systems can be compressed down to 2 rounds. Actually, let me ask you this. How come it doesn't work to compress down polynomially many rounds to 2 rounds? Yeah?
Because the 4 has to stay constant. For the n, you replace it with constant. For the negative n.
Yeah, that's one problem. Like basically the problem is error amplification. Like to really carry out these arguments, and whenever you switch like MA to AM, like you have to like amplify the error like again and like again and again, and to like get the error really down, you have to blow up the message lengths by a polynomial amount. So if you have to like do more than a constant number of like error amplifications, you like blowing up the message sizes by a polynomial amount super constantly many times. So it'll be like n to like a super constant length. So like we don't even know that like log many rounds compresses down to 2 rounds. Well, people have tried to think about that. Okay. Great. So let's save that and talk about the last two things that I want to talk about from the outline at the beginning of class. They kind of take us back from a little bit from outer space into like more concrete motivations. So remember, we started on this whole MAM business by asking about this motivation. Like, what if we just, at the beginning of complexity theory in the 70s, decided that efficient allowed for randomness? Okay, somehow originally people decided it should mean P. But now we're kind of used to randomness, and we should think about like what it means if we allow randomness. And several classes ago on this topic, we looked at this class, the polynomial hierarchy, and we came to this class by asking ourselves, like, okay, we probably don't think NP is solvable efficiently, but let's see what happens if it is. This motivation was like all the languages solvable efficiently if you assume that NP is solvable efficiently. And we saw that in that case, we talked about it in the context of P. Not only can you solve SAT, but you can solve unsat, and you can solve, minimum circuit problem, and actually quite a few problems that are not known to be in NP. Right. In other words, we have this theorem. NP is a subset of P implies the polynomial-time hierarchy is a subset of P. And OK, so we can now ask ourselves, well, what if we replace P by BPP? Does that imply, this would be your kind of guess / hope that all the PH languages are still efficiently solvable. And that's the theorem. It's proven by Zakos. And I'll show you the proof. It's not too hard. OK. So let's prove this.
Same as this. What's the difference?
You'll see when the proof starts, I think. Yeah. OK, so we're trying to prove this. Of course, we assume that NP is a subset of BPP. OK. Of course, BPP is close in their complement, so that implies that co-NP is a subset of BPP. Okay, you can always reverse your answers in BPP. Good. So now it's not too motivated, but I'll start out by considering sigma 2p. What is sigma 2p? We had this other kind of crazy shorthand for it when we invented it. We called it like exists for all p, which is similar but different from this kind of slash notation. But what it really meant was like, a language L is in sigma 2p if it there's a verifier with this property, x is in L, if and only if there exists some y, and then such that like a co-NP thing holds. So we can phrase it like this, such that x, y is in unsat. Okay, a language is in sigma 2p if it has this property. OK. Actually, this is not quite right. Let me just say it's in A, where A is in co-NP. OK, or I could put like a polynomial-time many-one reduction on x, y, and then ask if it's in unsat. Great. But under our assumption, co-NP is a subset of BPP. So this A, which is in co-NP, well, now it's in BPP. So now we have a different characterization. X is in this language if and only if there's some string candidate certificate that can be checked by a BPP algorithm. So this is exactly MA. Okay, so like by virtue of this and the fact that this check has been sort of upgraded from co-NP to like a BPP check, this shows that L is in MA. That's pretty good, right? We've made a lot of progress seemingly because we got sigma 2p down to MA. which is pretty good. Now, well, MA is a subset of AM. We know that unconditionally. So L is also in AM. And let's write the definition of L in AM. Actually, our very, very original definition of L being in AM was that like L is in AM if there's like a randomized reduction to SAT. So L in AM implies that there's a randomized polytime reduction R such that X is in L if and only if, actually let me write it in 2 steps. X is in L implies that with high probability R of X is in SAT, and X not in L implies that with high probability R of X is not in SAT. Okay, where R is a randomized reduction, so the with high probability is over like the coins of R. Okay, but now both these problems, determining whether the output R of X is in SAT or whether it's not in SAT, are in BPP by assumption. These are now both in BPP by assumption. So now we're great. Now L is in fact in BPP. Because the reduction can first do its random thing, and then instead of wondering whether it's in SAT or not in SAT, it can just use some further randomized algorithm to find that out itself. Okay, so maybe all along we have to like amplify error slightly because we have like 2 chances for error, that the reduction goes wrong and then that this decision goes wrong, but that's no problem. Great. So putting everything together, let me put the glorious conclusion like here. Okay, so therefore we've shown that sigma 2p is a subset of MA and AM, but then also BPP, subset of BPP. And one thing that we know about BPP is it's in the polynomial-time hierarchy. It's in, we proved this before, it's in sigma 2 and it's also in pi 2. Which is good. In fact, BPP is in MA, and that's in AM, and even that's in pi 2p. Okay, but this means that we finally got sigma 2p inside pi 2p. By taking the co, you have the opposite containment, so they're all equal. So they're all equal. pH collapses to the second level. But not only does pH equal sigma 2p and pi 2p, it also even equals BPP. Okay, so that completes the proof. I guess to answer your question a little bit, like the new ingredient is basically this proof that like MA is a subset of AM that lets you switch these. Yeah?
So like this basically, like our original assumption is that exists for all as a subset of for most. And so then you think of the polynomial-time hierarchy, you would replace all of them with for most, and then they'll collapse. Is that like syntactically how this works?
Basically, yeah. I mean, you have to just, the fact that you can do these replacements more or less relies on like thinking about the MA subset of AM proof. Luckily here, we were able to carry it out without like worrying gravely about those details because somehow you can pull it off just by knowing this fact as a black box. But yes. Okay. Now's the time where I have to like make one funny observation because like we're going to need this observation like 4 weeks from now. It's a crazy observation, but it's that this proof that I just finished doing relativizes. I'm not sure I really mentioned what that means before, but it's an observation. I guess I did mention this when I talked about the fact that the time hierarchy theorem relativizes. What that means is this is also a theorem. For all languages A, which are oracles, if and P to the A is a subset of BPP to the A, then PH to the A is a subset of BPP to the A. We're going to need exactly this theorem later when we prove Toda's theorem, which is about the power of counting the number of satisfying assignments to a circuit. And first of all, you might say, like, what does this even mean? Well, in the context of all these classes can be defined with these, like, exist for all things. So like, OK, this is a class. Really, this means that here, stuck into here, is like a polynomial-time verifier V. And the definition of all these relativized classes is that, like, it gets an oracle A. And basically, to agree with this observation, you just kind of have to, like, go back through all the proofs and just show that, like, if I change a V to a V to the A, like, everything would be the same. So, like, the error amplification is the same because, I don't know, like, you know, the fact that this is closed under polynomially many unions is also true if you stick an oracle in here. So, like, you kind of just have to look through the whole, like, last two lectures and be like, if he wrote V to the A everywhere he wrote V, like, it would still be fine. But it's good to make this observation now where it's, like, semi-fresh in your mind so that, like, when I bust this out, like, 4 weeks from now, you'll be like, whoa, like, should I believe you or not? Like, you're encouraged to see if you believe me, let's say, this afternoon. You can take my word for it. It's true. OK, good. Put that in the bank for later. OK. The last thing I want to do is, like, another kind of simple theorem. Like, it'll be, like, equally complex to this proof we just did, which is to say not that complex. But I like it. It's a popular theorem to mention because kind of feels like, OK, a lot of the times when I say, like, you know, oh, why are we studying these, like, crazy classes like AM, AMA? Like, what does this say about real computation? Just one sec. Like, you know, the reason we study them is because eventually they have, like, corollaries, or they help us understand, like, basic questions we have about, like, P and NP. And we'll see an example of that now. Yeah?
It would be a typical example why such a proof doesn't relativize.
Oh, like one homework problem you had like that where, yeah, you proved that, like, yeah, the HPV theorem does not relativize. But, like, yeah, up until, despite that fact, which was, like, known in the 80s, up until, like, the late 80s, complexity theorists thought that, like, pretty much every proof they ever wrote down relativized. And I guess it was true. Pretty much every proof they had written down, like Ladner's theorem and the time hierarchy theorem and, like, this kind of stuff, it all relativized, and it's pretty straightforward. But interestingly, the very famous theorem that does not relativize is the one that says, you know, general interactive proofs. So that's like, you know, polyround AM equals P space. That's a theorem you may have seen before. If not, we're going to prove it later in the class. But prior to this theorem, Fortnow, I think, had proved a theorem that showed there exists an A such that this is true. Now, I'm not so sure what to actually make of this fact because, first of all, it's weird notation, right? It's bad notation, right? If, like, x equals y, how could x to the a not equal x to the y to the a? It proves your notation is messed up, which it is messed up. You cannot relativize, like, a set of languages, which is seemingly what you're doing here. You're actually relativizing the computational model which generates this set of languages. So then it's, like, not exactly maybe clear the right way to put an oracle on a computational model. Kind of not a fan of exactly this stuff, so we'll talk about it later when we talk about this result. But that's an example of.
Are there any red flags in the proof that tell you that probably the proof doesn't go through?
Somehow, like, when one of the, you know, classes can, like, access the oracle in a way that the other one cannot, then you're kind of, like, worried. So that's what happened with this HPV theorem. Like, if you have, like, a low space machine, just doesn't have enough space to, like, write down, you know, like space n over log n versus time n. Like, if you give them both access to an oracle A, the time n machine can write down oracle queries of length n, and the space n over log n machine just cannot. Well, it can or it cannot, depending on how you define relativizing space models, which is why this whole business makes me a little bit queasy. But anyway, in the normal world, they cannot. And so somehow, like, there's like kind of like an unfair relativization of both sides. But it seems normally that when you have like these kind of standard proofs that involve, I don't know, simulation and repeating an algorithm several times and so forth, that it should have this property. OK. Hopefully I have time to prove this last thing. I guess I do, yeah. OK. So recall a thing that I told you, which is that graph non-isomorphism is in AM. Again, it's only clearly in a 2-round interactive proof if there's private coins. But next class, we'll see that you can get rid of the private coins. So just take it from me that non-graph isomorphism has an AM protocol. Okay? So another equivalent way to say that is that graph isomorphism is in co-AM. Okay? So here's the question that I think is like a nice question about life that everybody would want to know the answer to. Could graph isomorphism be NP complete? So note that graph isomorphism is definitely in NP. That's extremely clear, right? Like if you want to be convinced that two graphs are isomorphism, the certificate is an isomorphism. But could it be NP complete? And in fact, it's an anecdote goes that like Cook and Levin, published their Cook and Levin papers separately about NP completeness and stuff. And the anecdote goes that Levin like delayed his publication by like I don't know, more than a year because he was really trying to show that graph isomorphism was NP complete. And because pretty much every other like NP style question, he also showed it was NP complete. But like graph isomorphism, like he just couldn't do it, and like this was bothering him. So he had to like leave it as an open question. And well, technically it's still an open question. Now actually, a couple years ago, Babai, who's kind of like the hero of a lot of this story, famously showed that graph isomorphism can be solved in quasi-polynomial time. And that is good evidence that it's not NP complete. Because if it were NP complete, that means everything in NP could be reduced to a quasi-polynomial time solvable problem, which would mean all of NP could be solved in quasi-polynomial time, which is considered highly unbelievable. And it contradicts this like well-known assumption called exponential time hypothesis. But even before 2016, there was excellent complexity theory evidence that graph isomorphism is not NP complete. And I can tell you what it is. So remember actually when I introduced these, I said that like a general belief is that AM is actually equal to NP. And if this is true, well, that would imply that co-AM equals co-NP. And if graph isomorphism, which is in co-AM, were NP complete, well, then NP would equal co-NP. Okay, and in particular, that collapses pH. Okay, so this is considered pretty unbelievable. But this argument relies on AM equals NP. And that's maybe it's not clear to you why to believe it. In fact, the reason that people believe that is based on this hardness versus randomness work that also came much later than the 80s. So even if you imagine that AM is bigger than NP, which is maybe believable back in the day, there's still a reason, which I'll now show you, that you would think that graph isomorphism is not NP complete. This is called the Bopana-Hostad-Zakos theorem from '87. And it says this. If a language in co-AM is NP complete, okay, so like for example, if graph isomorphism were NP complete. By the way, this is equivalent to saying NP is a subset of co-AM. Then sigma 2, p equals pi 2p. Okay, and that's the hierarchy collapsing not to level 1, but to level 2, which is maybe still unbelievable. Actually, they both equal AM. Okay. The proof is only 4 lines long, so I'm going to go over by a minute here. Okay. So suppose indeed the hypothesis, which is equivalent to NP, a subset of co-AM. Well, that's equivalent to just co-NP as a subset of AM. Now let's look at sigma 2p. So again, it's basically like, the exist operator dot co-NP. Kind of like what we have exactly here, right? Okay, but our assumption is that our assumption gives us that co-NP is a subset of AM. So kind of exactly like we have here, it's sort of like this is a subset of exists AM. There's something Merlin can send such that an Arthur-Merlin protocol can confirm it. Okay, and that's the definition of MAM. Okay, but that's AM by what we did in class today. And what we did in class, last time is AM is a subset of pi 2p. So that's the end of the proof. Okay, so this is an example of how studying all these Merlin Arthur classes and sigma 2p and so forth can tell us, something, even back in the 80s when we had no other evidence, something interesting. Like graph isomorphism probably is not NP complete. Okay, so next class we'll talk about private versus public coins.